So hello everyone, this is lecture 70 for the mathematical physics. In the last lecture we have completed our 1D wave equation, and today we'll see 1D heat equation, that is also a partial differential equation. And the form of 1D heat equation is del u by del t equal to c square del square u by del x square, where this u represents the temperature and c square is equal to k by sigma rho, where this k is thermal conductivity and this sigma is specific heat and rho is density of material. So this is your equation. Now we need to solve this equation. For this, so let's see what this equation represents. So consider a thin wire of constant cross section and homogeneous material. It is oriented in x direction and is perfectly insulated laterally. So there is this single wire, or we can say it is one dimensional, and this direction is x. Then this thin wire has the same cross section all over the area, and we will see that it is laterally insulated, means no heat can pass outside this region, but it can pass from there and there. And we have put these ends at the 0 degree Celsius. So whatever temperature you will give to this rod will go to 0 only through the ends, means heat flow will be at the ends only, not from the lateral surface. Okay, so that's how the wave will be formed, means there will be some higher temperature, then temperature will vary in the whole rod with distance and with time, and that is the what we will study in this differential equation, that how temperature is varying with the distance and with time. Okay, so there are some boundary conditions. At x equal to 0, at all times this temperature will remain 0 and this temperature will remain 0. So we will put these ends at the 0 degree Celsius at all times. So at x equal to 0, at t it will be 0, at x equal to L, at t, at any time this will be 0. So this u represents the temperature, so this will be 0 at all times. Now these are the boundary conditions. Let's see some initial conditions. So at t equal to 0, whatever temperature is called fx. Okay, so it is called the initial temperature. And if this is equal to fx, then from the boundary condition f0 equal to 0, fl equal to 0. So these are the conditions we will use. So there is step 1, you know that we will use the product method to solve this differential equation. So we will assume u as f and g. So this equation will give you f g dot equal to c square f double dot g. So it is f g dot equal to c square f double dash g. Now separate the variables, take the f terms with f and g terms with g. It will give you g dot divided by g and c square equal to f double dash divided by f, and take these equal to some constant, that is negative constant, minus p square. Now we have two equations, first with this, second with this. So let's try to solve. First it is f double dash equal to minus p square f will give you f double dash plus p square f equal to 0. Now this is the second order differential equation. So you know the solution of this, fx equal to a cos px plus b sin px. Now use the initial conditions to find the a and b. So means we will use the boundary conditions first. So at x equal to 0, this must be 0. So at x equal to 0, this will be 0. So a must be 0. So we have found the a. So put a equal to 0 here. Then f at L will be 0 from here. So this a is 0. So now put in place of x L. So we'll get b sin PL equal to 0. Now b can't be 0, so PL must be n pi, and n is now from here you can, so now we can see here p is equal to n pi by L. Substitute here a equal to 0 in place of p, write the n pi by L. So it will be f n x equal to sin n pi by L x. Now let's see the solution for second one. G dot equal to c square g minus p square. So it will give you this. Now again you can solve this equation just separating the variables. This will go to first let's assume PC equal to lambda n, and then it will be lambda n square, and we know from here p is n pi by L, so it will be c n pi by L. So lambda n equal to this. Now this will turn out to be g dot plus lambda n square g equal to 0. Now this is a simple differential equation. So you just take g with the g dot and lambda n square to the right hand side and dt with it. So it will be dg 1 upon g will give you log g equal to lambda n square t, and then you can compare the terms. It will give you g and t equal to b n exponential minus lambda n square t. So this is some constant. Now see, you have solution for g and you have solution for f. Now you can write the complete solution, that is u n x t equal to f n x and g and t. So f and g. So this is your g, and this sin n pi by L x is your fn. So this is your u n x t. Now see, this is of any mode. Now you need to write the complete solution. So this will be sum of all the modes. So final solution to this problem is uxt equal to sum of all the modes, that is n equal to 1 to infinity. So u and xt will give you this. Now see, this is your solution. Now you need to find this coefficient of Bn. So how you can find this? So we will use the initial conditions now. So at t equal to 0, it will give you fx, that is initial temperature. So at t equal to 0, this will be equal to Bn sin n pi by L x. Now see, this is again the Fourier series we will use. We can directly find the Bn from here. Bn will be 2 by L, 0 to L, fx sin n pi x by L dx. So now you have your Bn, so that's how you can find. So this is your complete solution. Let's see some question based on this. So you have this rod, lateral insulated. Length is 80 centimeter and ends are fixed at 0 degree Celsius. This is your initial temperature is given at t equal to 0, ux equal to 100 sin pi x by 80. So this is your fx. And c square is also given. We need to find uxt. So see, we need to first find the Bn. So how you can find the Bn? See, this is equal to fx. So if you equate this to this, so at L equal to 80, we'll have 80 here. So n must be 1. Only then this will be equal to this. So B1 is equal to, you will see B1 will be 100 because this is your coefficient. So it will be 100 and all the B terms will be 0. So you will get only B1, that is 100, and Bn's are 0 for other than n equal to 1. So now you have your B and you have your n equal to 1. So just write it here. Uxt will be B1, that is 100 sin n will be 1 pi by 80 x exponential minus lambda n can be written from here. N will be 1, C is already given, L is 80. So you can write this also. So this will be your complete solution. So when you solve all the calculations, do all the calculations, you will get ux as 100 sin pi x by 80 exponential minus 0.0018 t. Now lambda n can be calculated this way. I already told you n is 1 here. So lambda is L is 80 and C is already given. So lambda 1 square will be this. Now see, if time increases, see with time this whole value is decreasing, means maximum temperature is decreasing. So at t equal to infinity, this term will be 0. So for any temperature, put any temperature here. If time tends to infinity, this will always reduce to 0. Why? Because this ends are not insulated. So there is always temperature difference, due to which there will be heat flow, and which will reduce the temperature always. So at t equal to infinity, always you will get 0 temperature in the complete rod. Okay, for this case particularly, when the ends are not insulated and the whole body is insulated. So let's take one more. So first there is one more part. How long will it take for the maximum temperature of the bar to drop down to 50 degrees Celsius? So first, this is our temperature. So when this will be maximum, first we need to find this maximum temperature. When this term will be 1, because this is only varying with the x. So this is 1, then this will be your maximum temperature. So now this is reduced, this is maximum temperature is reduced to 50. At what time? So we can find from here the temperature. Take the log, it will give you this, and time will be calculated as 388 seconds. So at this time, the temperature of maximum temperature will reduce to this. Now you can find that at what distance the maximum temperature will be. So we take the maximum temperature when this is equal to 1. So this pi x by 80 must be equal to pi by 2. From here you can find the x equal to 40 centimeter. At the x equal to 40 centimeter, you will have the maximum temperature. That will be reduced with time. Now let's take one more example. So you have this rod, again lateral insulated, and ends are fixed at the 0. So, and this is given, means this is your fx, initial temperature is given. It will be x, between x 0 to L by 2, and it will be L minus x for x L by 2 to L. So this fx is given. We need to find the u. So again, to find the u, you need to find the Bn, and Bn is given by this formula. And now 0 to L, this can be divided into two limits, because here fx is given in two limits, for the 0 to L by 2 and L by 2 to L. So we just write fx sin n pi x by L dx. This is the formula for Bn. So again, this fx is given x for the 0 to L by 2, and it is given L minus x for the L by 2 to L. Now you just need to solve these integrals and put the limits. This is very easy integrals. I am not going into the calculations. I will give you a direct result. So this is for the first integral, this is for the second integral. When you solve them, you will get this 2 by L, 2L square by n square pi square sin n pi by 2. So this will be your Bn. Now you can see that your Bn is varying with the n. So for n equal to 0, 2, 4, all the even terms, this will be 0. But for the odd terms, for 1, 5 9 it will be 1, and for the 3 7 11 it will be -1. So that's how your Bn will vary. So you will get uxt as this is your u, Bn sin pi by L x exponential minus lambda n square t. So Bn will be 0 for the even terms, so you will get only 1 3 5 terms, and here Bn is this, means square of that number. So Bn can be written in this form. For the 1 it will be 1 square, then you will get 3, for the 3 it will be 3 square 9, and all the terms will be there. You can calculate lambda n and all, so you can just write it the series. This will be your complete solution. So if someone said to you that plot these temperature at t equal to 0, so initial temperature can be plotted in this way, means if it is given at 0 to L by 2 it is x, so it will be a straight line. Then L by 2 to L it will be x minus L, sorry L minus x, so it will be negative slope, so it will go like this, and this maximum temperature will drops with time, so it will be somehow like this, and after some time it will be like this, then at infinite time it will be like 0. Okay, so that's how you can plot this with time. So this is at particular time, 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 this is at the 0 time. Okay, so this was given as the straight lines, but this will drop to this curve type structure after time. Okay, so let's see one more case for this. Now both ends are insulated. This time these are not means these are not at 0 degrees Celsius, but they are insulated, means whatever temperature you will put for the rod, it will remain as it is always, because there is no conduction. So it is literally insulated, and ends are also insulated. So this time see, there is no heat flow, so we can say that gradient of heat, what it means, that is change in the heat, is 0 here because there is no heat flow. So if we take the temperature's gradient, that is x, at x equal to 0, that will be 0 because there is no heat flow. Here also at L distance, heat gradient will be 0 for all time, but it can be heat flow in the inside the rod, but not at the ends or these ends. So that is a condition, boundary condition. Now initial temperature at t equal to 0, let's assume it is fx, and we already know from the previous that fx is equal to a cos px plus b sin px. This will not change. Now at any u will be fx gx. So now let's use the conditions. First we have these conditions for the gradient, so we have to use them. So for that we have to find this f dash x. So how can we find the f dash x? So let's take, we know u is f into g, so ux will be, means if it is taking you differentiation with respect to x only, so it will be f dash gt, and at x equal to 0 it will be 0. So now at x equal to 0, this gradient must be 0, so this must be 0. Gt is not 0, so this must be 0, so f dash 0 is 0. This is again a condition. Now this gradient at L, this must be 0 again, as here it is given, and again this gt can't be 0, and this must be 0, then f dash L is equal to 0. So these are the conditions we will use to find the constants, these constants. So let's see. Now this is f dash, so first let's find the dash derivative of this. It will give you cos minus sin pxp, and it will give you sin px cos pxp. So this will be your f dash x. So at x equal to 0, this will give you 0, and x equal to 0, this will be 0, this will be 1. So bp equal to 0, and p can't be 0, so b must be 0. So f dash L will be, means b is 0, so at L it will give you ap sin pl equal to 0, and ap can't be 0, so sin pl must be 0. From there you can find pl equal to n pi, and p will be n pi by L. Now this time n can be 0 also, because here you have in p, in place of p, you have cos function, that's why it exists for x equal to 0 also. So that's why we are taking 0 also here. Now gn is again same, you can just write an exponential minus lambda n square t. So un will be product of fn and gn. So f is this, and what is the value of this? We already find it this. So it will be cos n pi x by L, because it p is n pi by L, and put it here n pi by L, and a assume 1. So n pi x by L, this an exponential minus lambda n square t. So now uxt is equal to, means this is one mode, so take the sum of all the modes, then this will be your general solution. So that's it for today. In the next lecture we'll see that how can we find this coefficient for this kind of situation when we have both hand insulated. So thank you everyone.